Good afternoon. Okay. This week's lab deals with Avogadro's number, and you measure the value of Avogadro's number by using compounds of known mass to estimate the number of molecules in a monolayer. Good luck with that. Do the counting, okay? You need information such as molar mass, molecular geometry, and density to help you measure this number, 6.022 times 10 to the 23rd. So when you're done with counting, you can go home, okay? Good luck. The last time, we talked about mass spectrometry. We used mass spectrometry to get these ratios of masses of compounds. That's how we can relate the masses to each other and get the absolute mass. And we used mass spectrometry, and we had a combustion experiment where we combusted. Combustion means it reacts with CO2, hydrocarbon. Hydrocarbon is what we use in our cars, carbon and hydrogen compounds. Hydrocarbons, you combusted hydrocarbons in oxygen, and you've seen there was quite a bit of heat released. That means energy was released. And if we would assume now that we have caught all the reaction products, the reaction products are water and CO2. Hydrocarbon plus oxygen gives water and CO2. And let's assume we have caught all these reaction products, and we take now a sample and inject it into our mass spectrometer. So we want to get the ratio of carbon to hydrogen for this. So what we do is we get a ratio like this here, and this is the mass 18 and the mass 44. What would be mass 18 and 44? CO2, okay? And there is a ratio of 1 to 2. I'm asking you now, is this produced by methane, by acetylene, or by acetylene? Okay? Why don't you take your clicker and give me your answer, please? I know that you were all weekend thinking about this, nothing else but that. So you make water and CO2. And the water and the CO2 are in a ratio of 1 to 2, because it's double as high. So you have twice as many molecules or particles of CO2 than molecules of water. By the way, don't worry with your iClicker registration. If you click here, we have the number of your iClicker. All we need to do, link you to that number. And you do this yourself by going to iClicker to the web page and put your ID in there. Some of you have iClickers where the number is not legible because it's been there since eons, okay? And so the program works now. You can come to me after lecture, and I will give you the number of your iClicker. Bring your iClicker, and we test it, and I give you the number. That's not so good, huh? Okay, so B, some people say, and some people say it's C, and some say, oh, that's A, that's the simplest, okay? So why don't we think about this a little bit more? You need, if you make CO2, you need to have carbon. Each carbon gives you 1 CO2. So there you would have 2 CO2s, and there you would have 2 CO2s. You need 2 hydrogens for each water, okay? So you would have 1 CO2 and 2 waters here. Here you would have, and so you do it yourself, okay? Why don't you discuss it with each other and give me the answer? So each carbon makes 1 CO2 and 2 hydrogen makes 1 water. And you have a ratio of water to CO2, 1 to 2. Don't forget to click in. Yeah, we're getting there. That's good. That's good. Now let me explain it to you. So we make nothing at the moment. There would be one CO2 and there would be two waters if it would be methane. So the ratio would be 2 to 1 here, which you would see here, 2 to 1, water to CO2. That's not what we had. Now if the next one, what would be the ratio here? 2 CO2 and 2 waters. What would be the ratio? 1 to 1. So what is it then? So we make 2 CO2s and 1 water. 1 water and 2 CO2s, 1 to 2. And with this, the answer was C. Okay? All right. So this ratio, in this case it's right, but this ratio gives you the lowest, essentially mass spectrometry gives you the an empirical ratio, an empirical formula that's the smallest whole number ratio, because it's just a ratio to each other. It is not necessarily the formula number or the real structure. So how would you get the, now the ratio, how would you get the real structure? What do you think? Well, you take that hydrocarbon before you combust it, take a sample and run it through your mass spectrometer, and then it will show you the ratio, okay? And with this, you have the difference between empirical ratio, that's the lowest whole number ratio, that would be in this case CH4, in this case CH2, in this case CH. So in this one, it would be the empirical is equal the molecular formula, but with ethylene, we have a ratio of 1 to 2. That would be C2H4 would be ethylene, and acetylene is C2H2. It's a double bond in between. So there's a difference between the empirical and the molecular formula. Let me ask you that. Oh, let's do an experiment first. So we want to burn something else. We want to burn phosphorus in oxygen. And in the lab here, when we do demonstrations, we want to have a quick reaction. We use liquid oxygen. Okay? There's liquid oxygen in here. We will talk about this. Actually, it's blue, but you can't see it. And we use liquid oxygen in this reaction vessel. And there's phosphorus. You see that? See that here? That's one second. There's phosphorus there. I can't point to it. There's phosphorus here. And it's a piece of phosphorus. It's kept under oil because it's pyrogenic. It means if it sits around with oxygen, it will react. And so Karen has now put liquid oxygen in there and phosphorus. And now we need to get over the activation barrier. A little bit of heat, just a little bit. A heated rod will give us the reaction. So we make phosphorus oxide. We oxidize phosphor to phosphor oxide. Now let's have a look at this. Shall we turn the lights down a little bit more? Excellent. I can see you in the back. That's the Chem 1A light therapy, actually, for Monday afternoons. See, the energy is released in form of light. And there you can see yourself in here. So that's what they used in the old days in the movies. The beginning of the movies, they used sources like this. All right, later they came then with arc lamps. All right, and what you see, the white gas there, this is gaseous phosphorus oxide, which will eventually plate out on the walls of that reaction vessel. That's quite hot, isn't it? Quite bright. So, okay, if we can have the lights back, please. Thank you, Karen. See, the bear is glowing. So let me ask you a question. We have 30 grams of phosphorus and we reacted with 40 grams of oxygen. 30 grams of phosphorus and 40 grams of oxygen. And you see oxygen was a liquid first and then it became a gas to form a phosphorus oxide. What is the empirical formula of the oxide? What's the lowest whole number ratio? So phosphorus is 30 grams per mole, it's the molar mass. Oxygen is 60 grams per mole molar mass. So you can say this is about 30 and this is exactly 16. So now tell me, what is the empirical formula? Is it A, PO2, B, P2O5, or C, P3O4? Why don't you think about this and give me your answer? We're talking about molar masses here. You can do this in your head, actually. Okay. The smallest whole number ratio is the empirical formula. Wow. The morning class had this in one question. All right. So fortunately, we don't have too many people who say 3 to 4, because that would be not the molar ratio in this case. So why don't you, there's not much I can help you with this, because, I mean, this is 1 mole, and it reacts with 40 grams of oxygen. So how many moles is that? And then you have to have a whole number ratio, and you can deduce the formula. Why don't we do this again, and you discuss this with each other? Wake up, get the blood in the head. Discuss it with each other. Yeah, right.
Yeah.
So, but
Find the factor to multiply.
so what's the factor?
Double it.
Okay. What's the correct answer? Oh, you're done. Why don't you let me know? Hey, Nitsche, we are done. Okay? P2O5. PO2 is not quite correct, but I tell you why. So we have how much? We have 1 mole of phosphorus about. Okay? Oh, there's the phosphorus oxide. We had 30 grams of phosphorus and 40 grams of oxygen, but we need not mass ratio, we need molar ratios. So the molar ratio is 1 mole to how many moles is this? 1 mole is about 1 mole. You can estimate this. And this is 2.5 moles. So that would be 1 to 2.5. But this is not the right empirical number because it's the lowest whole number ratio. So you have to multiply this with 2, and you get 2 to 5, P2O5. And now I tell you, this is the empirical formula, and which you can't know. The molecular formula is actually P4O10, and I haven't asked you that. The molecule is a P4O10 molecule. Okay, so today we're going to talk about light. Light. Light, or the interaction of light with matter or with chemical compounds, is often used to deduce the position of atoms in molecules, or that means you determine chemical structure, or you use light to determine the energy of a certain molecule or atom. And light can be absorbed and can be emitted. Now the question we are going to discuss today is, what is light? So we know light is a wave. We just assumed this, and I'm going to show you today that light is indeed a wave. Light behaves like an electromagnetic wave, has electric and magnetic properties, and it behaves like a sinusoidal wave. All right? So there's our wave. And if you stand at the shore and you look at the sea, that's a very good comparison. There's waves in the sea. And as the waves travel through the sea, the speed which they travel through the sea, that's the speed of waves. And in our case, the speed of light is the speed of these waves as they travel. All right? The speed of light is abbreviated with c. And c is 3 times 10 to the 8th meter, so 300 million meters per second. Travels quite fast. So we can't change the speed of light. For what concerns us in this class, 3 times 10 to the 8 meters per second is the speed of light. Now, if you watch these waves coming in and you have 2 crests, and if you have these long waves, the 2 crests are very far apart. So you have a very long wavelength. The wavelength is defined as the difference between 2 adjacent crests or 2 adjacent troughs. That's the wavelength. Now, if you have long wavelengths, that means the frequency that the waves reach the shore is not very high. So they don't come very often to the shore because there's such a long wavelength. Now, if you have a shorter wavelength, the frequency that they come ashore is much higher. So they come much faster, much more often ashore. Not faster necessarily, much more often ashore. So we have the wavelengths, and then we have the frequency. And for light, the wavelength times the frequency is c, the speed of light. That means the wavelength is inversely proportional. If I put this over here, under here, c divided by nu is inversely proportional to the frequency, and vice versa. The frequency is inversely proportional to the wavelength. Okay? So our eyes, they're very limited. We can see a small portion of the electromagnetic spectrum. We see from about 700 nanometers. Nanometer is 10 to minus 9 meter. That's the wavelength, 700 nanometers, to about 400 nanometers. That's a shorter wavelength. And so it goes from blue to red, essentially. You have then the UV and the infrared, which we don't see anymore. And if you look here at the electromagnetic spectrum, you have here this visible light. It's a very small section of the overall spectrum of light and energy that is emitted from the sun. So you have low frequency, you have infrared, or you have microwaves, or you have radio waves. If you have low frequency, what do you have in terms of wavelengths? Very long wavelengths. And if you go to the other side, you have high frequency and you have very short wavelengths. You have UV, X-rays, gamma rays, and cosmic radiation. So we use those, for example, in medical procedures to visualize your anatomy and to treat cancers and so on. And the adjacent to our light spectrum is UV light and infrared light. So if you sit in your car and say, oh, wonderful sunshine, I'm going to get a nice tan, you will not get a tan. Because the UV light is absorbed by the screen of your window, by the window itself, okay? The heat, which is infrared radiation, comes through as hot as sometimes when you park your car and go into your car. So the infrared radiation came in, but the UV radiation comes not in, because, for example, I have these phototropic glasses. They change with the UV radiation. They get darker and darker. And so I sit in the car, and they don't work, because the UV radiation does not get through the light, okay? And so I have to get some under sunglasses, or I have to drive hanging out my head through the window. That's kind of, all right. So now let's look at this a little bit more scientifically. You have these wavelengths, they have a range, and wavelengths range from 10 to minus 16 to 10 to the 8th meter. So this is a very long wavelength, extremely short wavelengths. And you see the reverse behavior or the inverse behavior of the frequency. Frequency gets very high if the wavelength is small, gets very small if the wavelength is long. And this, as I've told you already, we are from 400 to 700 nanometers. This is what our eyes can see. That's all, not a whole lot. But we have ways to make things visible in other ways for us. So let's just talk about this light here, this white light. And this whole spectrum, from 400 to 700, even the whole spectrum, we see as white light. We see it as white. There's no color, all right? So many of you, or some of you have done this as a kid. You got a flashlight, and then you have a paper plate or a piece of paper, you poke a hole through there, and you put a flashlight behind there, and then you see, if it goes through here, you see a very bright spot here, and then it gets darker and darker and darker, and it diffuses. So because the light beam goes through here straight, and then it diffuses off the edges and becomes more and more diffuse until it's dark. You've seen that. Any flashlight does that, okay? So that's fine. We can do this, and you get something like this. You get an intensity distribution. This is our object here. That's our wall, for example. And you have, this would be a high intensity. You see that? High intensity. High. That means here would be the bright spot, and it gets darker and darker until it's totally dark as you go from the center outside. This is how you depict something like this. This would be an intensity distribution, or a probability distribution of the intensity. So now we have a second slit. You can do the same thing here. You get the same picture. Now you take both slits, two slits, and put your white light behind it. And what you get two high-intensity spots. One here and one here. It gets darker as you come here, and here it gets brighter again and darker. So you have two flashlights, paper plate or pie plate with two holes in there. This is what you see. All right? Not very interesting, actually, isn't it? But let's make it a little bit more interesting. If we use monochromatic light, this is light of one frequency, monochromatic light. This white light spectrum is, you see, it goes from 400 to 700 nanometers for what we can see. So this is polychromatic. It has many, many different wavelengths. That's polychromatic light. So what you see here, this light is made out of many different wavelengths that are visible to our eye. If you use monochromatic light, I have here a very cheap monochromatic light source. For example, this laser is 612 nanometers. It's a helium laser, I think, isn't it? And so you get, for $3, you can buy a monochromatic light source. And then I use sometimes a green laser, which is 530 nanometers. That costs a little more. It's $80. And they make some for a blue one, which costs a couple of $100 now. It's a big machine still. It's not very small. They make smaller ones, okay. So I'm going to get myself one soon, all right? So I can't justify buying a $600 laser in blue just to be ahead of my colleagues, you know. and so if you use monochromatic light, you get something totally different. But let's talk about monochromatic light a little bit more. You have these clear glasses, and you've seen the diffraction of light, of polychromatic light, into its individual components. When have you seen this? Recently, there was a great rainbow. For example, water drops, when it rains and the sun shines on it, they diffract the light, and different wavelengths will have a different diffraction angle, and so suddenly you see that whole spectrum from red to blue. And you see this beautiful rainbow. You see the colors in the middle, orange and yellow and green. You see this in the middle. So there was a diffraction. We displayed all the individual wavelengths, not totally singly, but we spread them out. Now, if you have a CD, most of you don't even know what a CD is anymore, probably, because you're MP3 guys or MP4. And so you use a CD and the light shines on there. You see that color on there. That's light spectrum. It diffracts the light. The white light is taken apart in its component. And so if you, for example, I gave you something like a CD, the white glasses that you have, use the white ones, look carefully at them. They have a concentric pattern of little grooves. This is a grating. And you don't have any glasses? How deprived is that? They will bring you some. Now look at this white light here. Okay, you see the colors? Yeah. So now you have the spectrum. You use your neighbors. Don't use the blue and red one, or green and red. So you see it? Okay, so we have diffracted it into individual wavelengths, and there it is. So you know now what monochromatic light is. So you have all the wavelengths there. They are lined up next to each other. All right? So if I could have the light back up. So if I take monochromatic light of one wavelength and do the same double slit experiment again, I put a monochromatic light source here. You will not get a pattern like this, but you get a pattern like this. So it will be very bright here. There are the slits. It will be very bright here. Then it goes dark. Then it goes bright again, not as bright as here. Then it goes dark. Then it goes bright, dark, bright, dark. And the same here. Dark, bright, dark, bright, dark, bright, dark, bright. So how come this happens? This proves that light must be a wave, because only wave have interference patterns. And let's talk about a little bit what an interference pattern is. If you have two waves and they meet each other, if they are in phase, that means the troughs and the maxima are parallel to each other, and they meet each other, and for example, the two maxima meet each other, then it makes a higher intensity. The intensity is doubled. Okay? It's the intensity of both waves, wave amplitudes together. So you get a bright area of increased intensity. Now you have where the troughs and the peaks are out of phase. You see this one has a peak here and a trough here. Now we have two troughs and a peak here and a trough here. No, you have a trough and a peak, I'm sorry. You have a peak and a trough here. So you add them up, there's zero. It's dark. You don't see anything. They annihilate each other. They extinguish each other. So you see nothing. So this is called constructive interference, and this is called destructive interference. Constructive means it gets brighter, the amplitude gets increased, and destructive means it zeroes itself out. So let me go back. So how did we get that pattern? No problem. So this light comes here and travels to here, and this light beam comes here, travels here, but we only have one light source. That's the first thing. And I will send you a little video where this is very nicely depicted, the whole thing. So I put it on B-Space, and you can click on it. So what happens here, this wave that comes here goes up, down, up, down, up, down, up, down, up. Okay? And this wave goes up, down, up, down, up, down, up, down, up. Okay? So you have constructive interference. You have constructive interference, and you get a very bright peak here. Now, let's look at this one here. So this wave goes up, down, up, down, up, down, up, down, up. And this wave goes up, down, up, down, up, down, up, down, up, down. Okay? So now you have destructive interference. So there is a dark spot. And so you do this, keep going. As you go along here, you can do this for this, you can do this for that, and so on. So you have constructive and destructive interferences changing. All right? So, for example, if we look at this one here, this is exactly would be one wavelength, wouldn't it be? This would be, that distance would be one wavelength. So this would travel here, go up, and this is a shorter distance. You see that here? Let's go to this one here. This is a shorter distance. Yeah, from here to here, then from here to here. So this would have to travel in order to have a constructive interference, a whole wavelength longer to interfere constructively. So it would go up, down, up, down, up, down, up, down, up, up. And this would go up, down, up, down, up, down, up, down, up, down, up. And it would, actually it goes to here, up and up, goes to here. But it would, this one would have to go a whole wavelength longer to get here, because that's the condition of constructive and destructive interference, and has to fit, okay? So with this, we have shown that light actually has a wave behavior, because only waves behave like this. You can see this when you have two pebbles in a very still body of water. You put two pebbles in there, and you see how they interfere. The concentric rings interfere, and they move forward in this direction. You see some very high, and some up. You have troughs, and you have crests, and the crests are in the middle very high, and they get smaller and smaller and smaller as you go, and it moves in this direction then. So let's have a look at this, please. I'm going to demonstrate that to you. We have here a helium laser, and we put it through a slit. It's monochromatic light. We put it to a series of slits, and what you see here, if we could have this up there, some of you will see it here. It's not so smart. Oh, I have a red laser too. And so you see here, this is the middle one. That's the brightest one. And then, now it's better here. Then you have a dark spot in there. Then you have a brighter spot, dark spot, brighter spot, dark spot, brighter spot. You see that? And it gets darker as you go outside. The amplitude gets less and less, or the intensity gets less and less. That's exactly what we have shown here. Yeah? If you cut this through the picture. So with this, I have shown to you that light behaves as a wave. And let me ask you a question. We have a two-slit experiment with monochromatic light, and we have wavelengths here. We get this interference pattern. And now I take a other monochromatic light source. We have a larger wavelength. So how would that interference pattern look? Would it look like this, like A, like B, or would it look like C? Interference pattern. So the wavelengths of them, I compare a longer wavelength than this one, and what picture would I get? Would I get this, this, or that? Let's get started here. So you all find now the lecture notes on BSpace and so you have no problems to download them? I assume that's true? Okay, good. I left you the old ones there, and I update them as I go along. They're essentially somewhat the same, but they're not absolutely the same. So if you want to know how the lecture proceeds, then you can look at those. Some people would like to download it, but I give you the newest one shortly before lecture, always 1 day before lecture, 1 or 2 days before lecture. Well, the number is increasing here. Superb. Excellent. Excellent. I'm proud of you. How can you understand? You had this all in physics or what? Good. You must have a good teacher here. No, you're smart. That's very good. Okay, that's exactly the right answer. Sure, it has to travel further if the wavelength is longer, then you get the pattern stretched out. That's why I explained it in such detail to you before, that you get this right. So let's go to the solution here. You see, you have this is not a big deal. So this will always be the same because the distance is the same, equal path lengths. But if you have here, now you have to have two ups to get this to the next point. Now, if this is spread further out, so that means that that wavelength has to be longer than before. It has to, the wavelength is longer, so it has to travel further. And with this, you get that pattern. And the longer the wavelength is, the more you spread it out. And with this, the answer was C. Excellent. Now, you can have the absorption of light. Absorption means it just takes the light and absorbs it and keeps it, maybe for a certain amount of time. And this is how we see, for example, this red. It's red, but it says Berkeley. This red sweatshirt here. It's beautiful, but not such a great color in Berkeley, though. But on the other hand, it's a beautiful shirt. So my eye gets everything reflected, gets reflected the red light, and the rest is absorbed by that sweater. Now, where's there's a nice yellow there, okay. Is there a yellow and blue one? Yellow and blue, anybody? This yellow sweatshirt there says Berkeley in the front? Okay, so that's a very pleasing color, actually. And everything but the yellow gets absorbed, and the yellow gets reflected back to me. That's how I can see that it's yellow. That's how that works, all right? So if you look at an absorption spectrum, this would be the intensity, and this would be from the spectral range from blue to red, what our eyes can see. We can do this for any spectrum, even if the eyes can't see it, but this would be not the visible absorption spectrum. So you see, if this is the intensity of the absorption, that means that all the green here would be absorbed, completely absorbed. The blue a little bit, there is a little bit of orange absorbed, a little bit more of red, and none of this magenta. You see, that is an absorption spectrum. If we look at emission, you can also emit light. A molecule or an atom or any substance can emit light. It must have gotten the energy from somewhere, but it can emit some of the energy as light, and this would be an emission spectrum. That's the intensity of the emission. That means it would be emitting very much green, so it would look green to a mixture of green and whatever here, orange to us, and there is no emission, so this doesn't emit that light, and so this is the absorption spectrum, it's the emission spectrum, okay? So this is just to introduce you to the intensity plots of emission and absorption. Now, you can also have a line absorption. If you have monochromatic light, for example, it absorbs certain wavelengths of that spectrum. And then you have a line spectrum. See that? That's a continuous spectrum, and this is a line spectrum. And so a compound or a molecule can also emit light of certain wavelengths. And then you get another line spectrum. This particular compound emits all these energies, all these colors here. And the colors are nothing but energies. And we talk about this later. So now take out your 3D glasses, please. Oh, no, I want to say, no, let's not take them out. I need Karen. Karen, okay. Karen, I need you here. You need to do this here. Yeah? No, not 3D. Let's do this first. Let's do it 3D. Okay. Let's do 3D. Okay. So 3D is the big fad. What do you like to say something? Or you want some glasses? Okay. So 3D is at the moment is a big thing. You have time. You will get it. Are there any 3D movies out there? People. Avatar. Did you get glasses? Avatar is in 3D. How fitting. So it screws with your brain. Okay, that I see you here, or you here, or you here is because my eyes receive a different picture. This eye sees a different picture than this eye. And of course, it goes back and forth all the time. So I have different pictures with each eye, and my brain processes these pictures, and with this here I can see you and you and you three-dimensional. Okay? Because the brain processes these two different pictures. So if you have only one eye, then you cannot have any depth vision. You cannot see three-dimensional. So this is what people use in these movies. They have essentially two pictures. Wait, not yet, I need to explain it first. They have essentially two pictures slightly off, superimposed to each other. In this case, one is red. That would be the left glass. So if I look through the red to red, I see it red. But if I look with a blue, it should be dark. Okay? And if you look at this, there's red. The pictures are superimposed to each other. The red goes on the left eye, the blue on the right eye. And you see it three-dimensionally. It screws with your brain, so to speak. I'm sorry, I shouldn't be saying this. It fools your brain, okay? Okay? So this is how we can get our brain to think that a flat object is three-dimensional. So let's look at another one. This is a buckyball. This is really blue and red, that picture. It's the perfect thing to do. And you see this is carbon-60. It's a fullerene, Buckminster fullerene buckyball. So my glasses fall apart here. And now we have another one. There's some organic molecules. You see them three-dimensional? Can see the depth? So it's not there. So that's Avatar Chem 1A, all right? Good. So let's go back and let's do an experiment. So I have here a white light source, and then I put it through a grating, and I spread that white light for you onto that screen here, that you see the spectrum of visible light, okay? And now what I said to you, if I put in a blue solution, this absorbs everything but blue, okay? Every other colors are absorbed, not quite two. I show you which ones are going to be absorbed, because if I put this in there, then it will absorb these colors, and only the color that this is here will go through. We ready? Okay. You see, the picture is here. You see, that is our spectrum here. We have dissected or diffracted the white light into its individual colors. And now I'm putting a blue solution in there. So that blue solution, it's not really only blue. It also has a tinge of green in there. You see that? There's some green here. So it absorbs everything else but blue and green, which makes it appear this funny blue to us. You see that? Now, if we use green light, a green solution here, you have to believe that the solution is green. We put this on, a little bit of yellow is coming through. What's happening? What's happening? Where is it? Okay, there it is. Okay, a little bit of red. So this is, it appears to our eye as green. Now we use red, so that the left side here, oh, that's beautiful. Let's see. The left side should go away. Sure enough, you see that? A little bit of yellow, and the red comes through. Everything else is absorbed. This is why we see this as red. And at the end, we do yellow. Yellow is obviously a combination of all kinds of colors. See that? It takes only the blue away, but it's a mixture of green and red and yellow and orange to appear this as yellow as a yellow solution. Okay, thank you very much. We can have the lights back up. You can see the solutions up here, the different colors. So this is how our eye perceives color. So it's actually a mixture of different wavelengths. So that's why we have different reds and different blues and different greens, because we can mix them. not only the colors, but the spectrum. So now I'm asking you a question, and the question is, we have an object, and this has an absorption spectrum. So you shine light through it, just like what I did here. And this light shines through, and this is your absorption spectrum. So this is the intensity here. So the intensity is 0. That means all the light goes through, and no light goes through here. So, and very little, a little bit goes through here. So what is the color of that object? Is it mostly blue, mostly green, or mostly red? Why don't you try to answer that? No discussion yet. Hey. Figure it out if you can do it on your own first. It really doesn't matter, but it would be a good thing, good test for you to see if you have gotten the concept or not. What is it? Yes! Excellent! Excellent! Good class! Must be the teacher. Not really. Somebody said you don't get it? Okay, so it's 16%. Usually I don't 20%, but let's do that. We want to make sure that we have success here. All right? So this is our absorption spectrum. Now, does it absorb this orange and red here? Does this get absorbed? So this is gone. Does this get absorbed? Not as quite as much, but it's essentially gone. Does the green get absorbed? Yeah, but that blue and the green here, the blue and the violet here, we didn't even go that far, doesn't get absorbed. So what does it mean? It goes through. And if it goes through, what color does it have? Blue. See, there it is. It goes right through there, and the color is blue. So with this, I'm going to see you on Friday. On Wednesday, I'm not here. Greg Dellinger will be giving the lecture, and the head TA. And please return the glasses. They are very expensive, not for you, but for us. We need them back, please. Okay? You get much better glasses in Avatar.